Thanks so much for joining our paper reading today. We have a really great paper on multi-agent fine-tuning, and I'm so excited that we have one of the authors of this paper with us today. Yilun, do you want to give a little bit of an introduction?
Yeah, sure. Yeah. Hi. So I'm Yilun. I'm starting as an assistant professor at Harvard in a couple months, and currently I'm a senior research scientist at DeepMind.
Awesome. We're so excited. Thank you so much for joining. So for today's kind of flow, what we're going to do is we're going to cover kind of the latest AI industry updates or update really for the last 2 weeks. I'm going to give a little bit of an overview with Elon's help of exactly what the paper entails. And then we're going to have like a really great question answering. I've got some questions. I'm sure you all have some questions. So we're really going to take advantage of having an author here with us today. So with that, let me get started. So industry updates. I think there's really one update that everyone really, if you're not aware, should be aware, and that is the release of DeepSeek R1. So what is this? This is an open source large language model. It's very comparable to OpenAI's O1, and it's coming from a startup out of China. So why is this important? What's the impact here? And there's a few things that I think are notable. I think one thing is the fact that they actually are able to reduce the cost and computational power requirements for this model by only activating the parts of the model that they need for each query. So that's something that's kind of unique to this model, something that's really shaking things up with the models that we've seen so far. It also challenges the belief that you need like substantial financial and computational resources for these kind of advanced AI developments. We don't really know the exact numbers of like O1. Or like 4.0 even. We know like 3.5 and 4's training, but we believe that, the newest models, even GPT-5, the unreleased model, is supposedly very expensive to train. So this really challenges that you need that much money to build a model with, comparable performance. So I think that was interesting as a result of all of this. NVIDIA's stock dropped like 17% on Monday. I believe it's back on the upward trend, but because they're saying they don't need the, most advanced chips, that definitely had some effects on their stock. And it was the most downloaded app in the Apple Store for a while. It was like the ChatGPT app. Like immediately after release, this was like the most downloaded app. A lot of US users using it. So I think it's just interesting to see. The industry has kind of been stable with these kind of clear winners, these clear top contenders for models, and with this release it's definitely changed things. Little bit of a heads up, we are going to do a paper reading on this in about 2 weeks, so definitely come and join us. I think it'll be a really interesting one. We'll take a look at how you can use this model, what the performance looks like, doing things like evals with it. So I'm pretty excited about that one. Cool. So with that, I see we got some yeah, okay, so we have some questions about DeepSeek. We'll save those for next week. Definitely join us and we'll get into those. So cool. Let's talk about multi-agent fine-tuning. I'm gonna cover this slide, but Yilun, definitely join in. Let me know if I missed anything. You're the expert here, not me. I know we're gonna give you lots of questions, so trying to give your voice a break here. But I really think that the main challenge that you all sought to kind of address is the fact that language models have this kind of diminishing returns after you kind of iterate on fine-tuning. There's these diminishing returns, performance kind of plateaus. So you all kind of sought out to say like, well, how can we improve this? What is the correct way to improve performance through this self-training? So you all introduced this concept of multi-agent fine-tuning. So we have these multiple models starting from the same base, independently fine-tuning. I definitely would love in the next slide you to go through a little bit of that kind of the multi-agent debate and how you all created the training data set. I think that's really interesting. So what this does is foster diverse reasoning patterns, and then we see sustained improvement over multiple training iterations. So those are some of the key ideas here. Again, moving a little fast because we're going to get into it all. And I definitely recommend you all read the paper. So let's talk about the methodology. So instead of one model improving itself, we have a team of models that learn from each other. And so, Yilun, do you want to kind of talk a little bit about like how it works, the methodology, how you use kind of different models to do the critic and synthesize models, all that good stuff?
Yeah, sure. So at the beginning, we start with a single base model. And once we have this base model, we essentially take this base model and we copy it a number of times. And we make some of these copies of these models generation agents. So these models are responsible for generating different possible answers to a problem. And then we specialize and make a set of other models specialized on criticizing or like trying to refine answers. So once the second set of models sees the answers generated by the first set of agents, and then it learns to construct, it tries to construct a more accurate answer given the responses of all the other agents. So essentially we have two populations of agents, a set of generation agents, and then a set of critic agents. And then what we do is to specialize each of these models, we have each of these models generate an initial set of responses. And then we find the answers that are like, by taking the majority vote across all these models, we can find an overall consensus answer. And then what we do is we then choose the initial answers from each agent that match the consensus answer. And that allows us to get task-specific data per agent. And we repeat this a bunch of times over multiple training iterations. And the idea is each agent is roughly trained on the data that's generated by themselves, generated by the agent itself, as opposed to like the same corpus that every other agent is trained on. So over training time, the agents learn to specialize, and you get different reasoning paths.
Super cool. Yeah, I think this is really interesting, and I'm just going to skip ahead to the next slide because I think that's really like it tells the picture really well of like what this means and how this impacts performance. So you can see here these are three of the models that I believe you all used. I think there might have been a few others that you tested with as well, but this bottom line here, if I'm understanding correctly, this is like your typical training iteration. If you were just going to use that single agent and try to kind of do these multiple rounds of fine tuning, you're going to see this plateau, if not like drop in performance. But with y'all's approach, you can see as you guys kind of do these multiple iterations, we're actually seeing that performance increase over time. And this is on one of the data sets, but I think this really speaks for itself here of the impact of taking this approach. That's quite a large, change in performance you can see. But anything else you would want to kind of call out on this, on the performance that y'all saw?
No, yeah, I think one big idea is like whenever everyone does a lot of fine tuning, people usually consider I guess people usually just consider like using a single model. I guess this tells a story about how we can actually by like just like even taking the single model and like making multiple copies of it and then fine tuning specialized models based off that can already improve the performance. And yeah, I guess there's a question where
Yeah.
are all the models using the same LLM? So we do initialize all the models we use in this multi-agent setting from the same base model. So it would be interesting to actually use different models at the beginning and then try to fine tune some.
Yeah, maybe a potential, next step for y'all. Okay, cool. I'm gonna stop sharing here because I got some questions written down that I know I want to ask. For everybody in the audience, any questions that you have, send them our way here because we'd love to be able to ask, since we have an author here that's something special. So I think we can kind of start off maybe with something kind of, I think maybe like a simple question of just like while y'all were doing this, what were some of the like big technical hurdles that you guys had to overcome with this approach?
Yeah, so at the beginning, when we were trying this type of multi-agent fine-tuning, what we found is that agents didn't converge to very different responses. So the initial thing we did is we again had different sets of networks with different weights. But what we did is we just simply trained every single model on all the correct responses. And what we found is that if we train all the models on the same data set of responses, then over the training iterations, the model's performance we didn't see as much consistent gains after multiple rounds of fine tuning. What we found is that the diversity between agents started dropping over time. So we found that, so I think one big hurdle was actually just like figuring out a way to make it so that the agents are more specialized. So our method is just to train each agent on only the data it's generated that is correct. But there's a lot of possibilities of additional methods that you can use to get even more diverse responses. And I think that's a very interesting direction of future work.
Yeah, that's super interesting. So it sounds like you did experience some cases where the agents were kind of converging or had like similar reasoning paths. How did you kind of maintain the diversity? Was that kind of using, the kind of debate approach and how you're describing the critics, how they created the data and only choosing, specific outputs?
Yeah, each agent when given a question generates an initial response, and now we take all the responses from the agent that are correct with the final consensus, and we only train it on that set of responses. So we don't train it on any other data that other agents generate. So as a result, each agent is gets continuously trained on different subsets of the data that it generates. So this encourages a lot more specialization among the agents.
Yeah, that's really cool. I think we have a question here in the chat here. So how would you improve multi-agents coordination problem as it's equally important to improve individual specialized agents?
This is, improve I'm not sure if I completely parsed this question correctly, but I guess, yeah, maybe one question is, on one hand, we have like two maybe competing goals. On one hand, we want to make a single agent as good as possible. And on the other hand, we also have this goal where we want all these agents to cooperate together to generate a better response. So I guess the way we did it is like the way we designed our cooperation mechanism is that when each agent improves a lot by itself, it also leads to better cooperation. So I guess we shaped this cooperation to be that each agent should try to be as accurate as possible on the first round, and then on the second round, all these agents should try to get as accurate as possible answers given the first round of answers. But I guess you can imagine there are many other ways to also structure cooperation between the agents, and then it gets a little more complicated because now you have to try to get the individual base models to be more accurate while like kind of maintaining so I guess you want the overall system to be more accurate, but maybe it's not necessarily the case that you want every single agent to be as accurate as possible. And I think that's an interesting direction of future work that we didn't explore too much in this paper.
Gotcha. That makes a lot of sense. Yeah, we have some questions about use case. I think we'll save the use case stuff for later. I've definitely got some questions too on how this relates to the real world. So we'll definitely get to that one. I think something you kind of been describing is it sounds like there were some kind of unexpected maybe papers, or maybe y'all did expect them during this kind of multi-agent interactions. Anything worth noting there of like something that you all felt was unexpected that was impacting the performance?
Unexpected. Yeah, I think the diversity was one big thing. What else? Well, one thing we found is that if we use the fairly narrow data set, it seemed that sometimes the models would, I guess, overfit a little on your training data. And then what would happen is the performance wouldn't necessarily, like as you did more rounds of fine tuning, I guess it depended on how big your data set is. What we eventually converged on is we had a training data set around 1,000 examples. And this was sufficient enough that it encourages models not to overfit too much on the particular examples you saw. But we did find that if you use very few examples, which is sometimes like due to GPU resources, that's the easiest thing to do. We did find that this didn't work as well, although we found that every type of self-improvement method didn't work so well. So it seemed that you needed some amount of base number of problems before things started working more smoothly.
Oh, okay, interesting. So those base self-improvements kind of had to kind of iterate from there and evolve on those original improvement methods. Very cool. I think there's some questions here about how the agents are communicating with each other. Can you talk a little bit on how that
Yeah,
works?
so the agents currently are communicating straight through English. This is, I guess, the natural medium in which the models generate. It would be interesting to also like potentially prompt the models or like specify that the models output in JSON, or you could imagine some type of latent space also. So I think there are a lot of things that could be done on like what exactly is the way to communicate between these models.
Yeah, that makes a lot of sense. I've kind of seen from my own experience of playing with these, it seems like a toss-up. Sometimes English is just the right way. Like you said, that's kind of like the native way for these models to interact and how they kind of produce. But I think sometimes structured has its benefits. So would be definitely some interesting research. We got a question here about the difference between agent fine tuning and normal LLM fine tuning. They want to know if there are the similar techniques that you would use for like traditional LLM fine tuning you could use here.
Yeah, I guess we overloaded the word agent and model. So when we refer to agents, it's actually just the LLM. So each when I say we have like multiple generation agents and multiple critic agents, actually each agent is just the LLM. And you would use the exact same techniques for training the agents as you would LLMs because it's just a set of weights for a network.
Gotcha. Yeah, I feel like that's something these days becomes more and more confusing. What's an agent? What's an LLM? Some people use them in different ways. So definitely thank you for clarifying on that. Let's see here. Um, okay, so I think there's a lot of complexity with this it's actually quite simple, but there's definitely more complexity than just, fine-tuning a single model or, skipping fine-tuning altogether. Was balancing kind of trade-off something that was important to you all, or you were just kind of really focused on the quality of the output? Anything there you had to really consider?
Sorry, could you just rephrase? I think my connection might have cut off so slightly. Could you just repeat it? Yeah.
Yeah, no problem at all. I was saying how this is kind of like the multi-agent fine-tuning, it adds some complexity to like a training pipeline versus, a single agent. And I was curious, there's obviously trade-offs between like computational costs, like number of agents. But I was curious if you all like balance those trade-offs or if you all were really just focused on being able to produce really high quality
Yeah,
outputs.
makes sense. Yeah. So I guess our overall goal was we really wanted to see some type of consistent self-improvement over multiple rounds of fine-tuning. So what we found a lot was like just single agent fine-tuning was that it really seemed like after 2 or 3 rounds, the performance just started dropping.
Mm,
So I guess the thing we really wanted to focus on is having like these much more consistent rounds of improvement.
yeah.
So we didn't spend as much. So I guess we didn't really tune the hyperparameters of number of agents or like number of rounds too much. We actually just used 3 agents and 2 rounds.
Okay.
But yeah, our overall goal was just like whatever technique that we could use to really get like much more consistent self-improvement over time.
Gotcha. So that was the real goal. Didn't really care about tuning those other knobs there. It was just really about that, which makes sense. That's the focus. And I think you all definitely accomplished that goal. The outcomes here are really stellar. Um, I have an interesting question I think is important, and I think you guys talk about it a little bit in the paper. Why do you need the multi-agents? Can we do this with just one single agent or one single model?
Um, so I guess you could actually, so one thing you could do is instead of using, I guess, a single model, you could actually imagine that like when you prompt each of these models, you get like different agents, right? And then you could just fine tune the weights of a single model. So I think some of the ideas in this paper could actually be used also even with a single model setting without multiple models, where I think that still the idea is that you want to train the model to think in a couple very different ways.
Yeah.
And then you want to like consistently reinforcing the model that you want to think in these very different ways. So I do think some of these techniques do not necessarily have to be exactly used on multiple agents. They could also be used on single agents.
Awesome. That's really interesting to hear. I think that might be something that's a little bit more, um, you know, accessible a little bit to some folks rather than having to deal with, multiple agents there. All right, cool. All right, so I think this is probably the part where you'll focus on use cases or focus on the real world because I think that's what a lot of our audience cares about. I'll go back to a question we got from one of our audience members earlier, and they want to understand some of the use cases that can be kind of come from this type of paradigm here. Any thoughts on that?
Yeah, I mean, on one hand, I think one use case is just like, let's say you want to do better reasoning with these models, or like let's say you want to do more accurate like even like language generation, or you could imagine that maybe you want to do more accurate proofs. But I guess most things, the most like outputs that you want to generate with an LLM, you can roughly formulate as some type of I guess generation plus some like objective function you want to optimize. And I guess roughly we have a set of models that generates different possibilities, and then we have a set of models that critiques and chooses the best possible ones from the original models you generate. So I guess in my opinion, I guess you can roughly use this for any type of real world like reasoning use case or I guess another way to think about this is actually any type of setting where like you want to fine tune your LLM for that particular setting. Well, instead of fine tuning a single LLM, now the idea of this paper is just that now you can just fine tune multiple different models, and then you also train the models to like critique the responses of previous models. And the combination of fine tuning a large set of models as opposed to single model seems to give you a more accurate performance, especially if you want to like like you maybe you want to like several rounds. If you have a bit more of a budget to fine tune the models, like this can give you a bit more more reliable answers than like maybe just fine tuning a single model.
Totally, that makes a lot of sense. And I think as these use cases, and we seem particularly with the world of like an agent that's using tools and having multiple steps and following all these steps to accomplish a task. I think reasoning is something that I think we keep coming back to as being like super important. So I can definitely see this being helpful in a lot of use cases. That being said, did you all kind of test this with any like more real world scenarios, or just kind of focused on those tasks that you use to kind of benchmark this approach?
Yeah, I guess we were very focused on reasoning. I guess we were yeah, we didn't really try testing it too much on more real world use cases. I think that would be a very interesting setting to explore further. Yeah, we were just very excited about this idea, like how can we do self-improvement in reasoning?
Totally. Yeah. No, I mean, it's very exciting. I think really when I was reading this, I was like, this is really cool. And I see so many different applications, so many new research avenues we can take with this. I think self-improvement seems to be something that the community keeps coming back to. And in my opinion, this is one of the like realist, I'll use the word, or tangential kind of or tangible, sorry, examples of it. So I'm definitely excited to see where this goes. There's a question of how this compares with the latest reasoning models. I think we showed kind of in we don't have O1 in here. I don't know, I don't remember if there was a graphic in the paper, but yeah, any kind of thoughts on like the latest reasoning models, how this compares?
Yeah, I mean, I think this is I think it's a slightly different way to scale reasoning compared to I guess some of these like O1 style. One way I kind of view this is roughly everyone's working on different ways to scale test time compute, and I think like in this type of way of scaling test time compute allows you to do better reasoning. And now one way is if you do some type of reward RL on some type of reward function, you have these like very long chains of reasoning, and it's on a single model, and that can allow you to do a bit better in reasoning or like it can allow you to solve problems more accurately. But like you're not really limited. I guess the statement of this paper is you're not limited to a single model. You can actually
Yeah.
have many of these models do these different chains of reasoning, and then you can imagine that you have many models then verify the responses on all of these initial generation chains. So this gives you additional access to scale up your compute beyond just even doing a single chain. So I would imagine these are kind of synergistic ways to really scale up the reasoning ability of models.
Totally. That makes a lot of sense. I there's a question here that I really like, and I think it's an interesting one to talk through. They're asking for your take on what you feel like is lacking from having a full-blown agent revolution. So yeah, any takes on that?
Yeah, I mean, I feel that right now when we're doing when we talk about like language model agents, normally we just like prompt the model with a couple examples, or we just do some amount of like targeted fine tuning. And I think that there is a fundamental difference between like making decisions in the world and like maybe like predicting like the class of an image or an object. And the thing is, when you're making decisions in the world, you really have to have this, you have to really plan, like you have to construct a sequence of actions and model what will happen based off your current action. So I think the very big difference between having like a constructing intelligent decision making agent versus like maybe supervised learning is that you have to do a lot more search or planning. And I think that needs to be done. And you can do this with some type of reasoning, like kind of maybe this O1 style, but I think you really need to have something where you have a little more deliberative. Let me generate these actions and then let me simulate what the outputs of these actions are and like how much these actions actually are towards my intents and goals. So like having a bit more of a explicit decision making knob inside these language models, I think is really crucial to getting like a full blown agent revolution. And I guess like a lot of this like multi-agent fine tuning as well as also like this O1 stuff, like they're all about like building a bit more reasoning. But I think like building a bit more explicit like model based reasoning, like reasoning about like the effects of your actions and how they achieve go towards achieving your goal would be an important step towards actually getting intelligent agents.
Yeah, that makes a lot of sense. I think research like this is going to continue to propel us in that direction. I think you're absolutely right. We've seen it even with like the simple things of using like chain of thought prompting. Like you see the difference in when you're able to have kind of instruct the model to use reasoning, the benefits there. So I think that like model-based reasoning that you're talking about is a super interesting concept and could potentially have really cool implications. All right, we got about 5 minutes here. Let's see. I think something that would be interesting. I know you said you didn't really test on real world scenarios, but you definitely think that any kind of task that requires reasoning would benefit from this. But do you think there's any consideration folks should take if they want to kind of use this approach and translate it from, research into a production environment? Any steps or considerations you think that they should take?
I guess one big consideration is like how exactly you store the infrastructure for running multiple
Okay.
models. So you can parameterize these models with like some type of low rank adaptation, in which case it's pretty easy to deploy multiple instances of this model. But I guess in terms of deployment, I guess there's a number of maybe more performance considerations. So in contrast to having a single language model, now you have to load many different weights. So now you have
Yeah.
to, now there's a bit more of a serving cost. But I guess outside of like maybe the cost, I feel that the method, we at least found the method to work pretty well across a different set of domains. And the training procedure is relatively straightforward. So I think if you're willing to like spend a bit more cost in terms of inference time and maybe training time, then this
Okay.
seems like a reasonable setting. And I think this is pretty reasonable in settings where you want to do reasoning. Like I do think the cost you get from this approach is probably a much less than the cost you would get from like some explicit reasoning model, because the number of total generated tokens is much fewer. But this is somewhere along the axis of like cost versus like maybe reasoning performance.
Gotcha. And someone did ask actually, speaking of costs, they're curious about the cost of this technique, how it stacks up. And I think cost, we talk about cost, it's a lot of different things. I think it's latency, it's time to generate tokens, it's the actual dollar amount that you have to spend to fine tune. So yeah, any thoughts on how it stacks up against other techniques?
Yeah. So I would say that it's definitely much slow, maybe more expensive than like just calling a model once and getting the answer. I think it's much cheaper than like some type of like a deliberative like thinking model, like this RL style stuff. It's both much cheaper to train as well as much cheaper to infer. So I would say like it's maybe like so let's say you have a total of 6 agents, then it will be 6 times more expensive than like querying the model a single time, but not like 100 times or like 1,000 times more expensive. So similar to some of these reasoning models.
Totally, that makes a lot of sense there. So that's good. It's like more of a 1x than a 100x. So that's always a good approach. All right, cool. I know we have just a few minutes. I kind of want to take this of like what's next. I know that you all might have some research, but I want to hear what research you're planning, what you're excited to see in this field, as well as what you really feel like the involvement of the self-improvement of AI will really end up being.
Yeah. I mean, I think towards the maybe the second question first. So I feel that normally when we talk about self-improvement right now, we talk about okay, we have some type of reward function, and then we maybe run some type of RL on top of it. I think that if we, I guess if we like, for instance, look at society, when we have a lot of people, and then we have a lot of people interacting with each other, now we get a much more sophisticated society than like any other single agent. So I feel
Sure.
that this idea of having many models is a way to really get like much more like drastic self-improvement, is my belief. And I think that also like. In general, in terms of thinking, like if we look at our brain isn't like a single giant model. Like our brain actually has a bunch of different modules that kind of interact with each other. So I think that the way to get intelligence is really to have a bunch of these like decentralized models and having some type of communication between these models and having that
Yeah.
communication be the like essence of like maybe intelligence. So I feel that like how like reasoning or like just general thinking or solving problems should be like many different models communicating with each other. And I don't think it needs to be language, but it should be some type of medium of like many models and communication between them.
And I agree with that. I even put like a little analogy in the slides of like, if you can think of it as a group of experts, each focusing on different aspects of a problem, it's going to be a lot stronger than a single expert alone trying to accomplish a problem. So I totally agree with that. But yeah, last minute, what's next for you? What are you working on? What are you excited about in the industry?
Yeah, I mean, yeah, I guess I've been very excited. I feel maybe the overall, I'm very excited about just generally reasoning. I feel that like this type of RL reasoning, it's like maybe a step towards reasoning, but I don't think it's the full solution. But I feel that having systems that can much more deliberately reason, like I think having some type of verifier, like being able to tell whether an answer is correct and running some type of search on top of that. But in general, like building a bit more reasoning into these models is maybe the most exciting direction. And I think that that can like do a lot of things ranging from like having intelligent agents to having more accurate factual answers to like having like better physical robots. So I think that a lot of the things that we're missing right now are due to the fact that the current set random models can't reason. But also, I don't think that we have the right tools for reasoning at the moment. And it might not even be an LLM. Like I don't know. It's like it still seems like we are pretty far away from actually getting systems that can like more systematically reason.
Yeah, totally. Well, it's an exciting time. I think there's a lot more to come, a lot of advancements in a lot of different areas. So we'll definitely be watching out for your research. I know folks are wanting to connect with you on LinkedIn or an email if you want to drop it in the chat there for them to find you. But thank you so much for joining. Like I said, this paper was really interesting. I'm excited to kind of try it out with my own projects. I'm sure people in the audience are definitely excited to try it out themselves. So thank you so much for driving or for coming and help driving this research forward.
Yeah, great. Yeah, thanks for having me. Yeah, great.
Nice, anytime. Thanks,
Okay.
everyone.
Okay, thanks everyone. Okay, see you.